Welcome at today's Tech Talk from Veldhoven. A special welcome to our colleagues from Asia, which is the reason that we start at 9 o'clock in the morning in the Netherlands, because it's in the afternoon in Asia. Our Tech Talk program is aimed at all our colleagues and is intended to provide some inspiration for all who is busy with technology. And my name is Wim van der Zande, and I sponsor the Tech Talk program together and organize together with our team here in Veldhoven. Today's speaker is Professor Heino Falcke from the Radboud University Eindhoven, Nijmegen, Radboud University Nijmegen, and also professor at the Max Planck Institute for Radio Astronomy. His studies and research brought him to many distinguished places, and I think that a common factor in all his research and themes have been interferometry and radio astronomy, and he's reached great heights in that research. Many years ago, he started his ambition to create an event horizon telescope in order to learn more about the most mystical things in our universe, the black holes. And now, many, many years later, and establishing an enormous international consortium, he has achieved great success with this, and that makes it a great pleasure to have this subject here. As an individual, Professor Falcke has also not gone unnoticed. He is an author of a best-selling book, at least that's what I read when I opened the internet pages, with the title Black Holes, the Universe and Us. And not only that, but he's also in the possession of an honorary doctorate of the Faculty of Protestant Theology and Religious Sciences. So to stress a little bit the scope of Professor Falcke in his work and in the world. So it's an honor to give the floor to the speaker, who will be looking at black holes 53 million light years away, which have a size such that it is almost comparable if we would have an overlay of about 0.1 nanometer on our wafers. So impressive it is. I give the floor to Heino.
Thank you so much for having me here today, and I'm glad to talk to you about black holes, my favorite subject. And I want to take you to a trip to the end of space and time. That's how far we've come, and that's what we've been able to see, I would say almost with our own eyes, but it's actually through radio eyes that we can see them now. And this work is work that I've been working on, I think, for 25 years, and it's been come to fruition, but it's only the first step we're still doing. So it's a long journey that we're making. I'm doing this together with a lot of colleagues, of course, with my colleagues at the Radboud University, where we have the radio lab, started a couple of years ago to support me with the technical work. We were funded by the European Research Council for, with funding excellent science. And overall, it's actually a global collaboration of people where the Netherlands are participating in. Certainly, the Radboud University, where I'm working, is one of the stakeholders. And here you see a collaboration meeting that we had in 2018 with actually 120 of the scientists, of the 350 scientists that make up the Event Horizon Telescope, and which consists of 13 institutions in Europe, in America, and in Asia, which came together to make this happen. And this meeting actually took place in Nijmegen, and this was where we actually prepared our publication, our first publications with our first results of the first image of a black hole. So everybody is smiling on these pictures because they already knew what was going to come out a couple of months later. Now, let's talk briefly about gravity. And as you probably all know, our view of gravity has changed. A very fundamental insight came from astronomy in the beginning, namely the orbits of the planets around the sun. It was easier to describe the solar system by having the sun in the center and the planets go around. And Newton was the one to able to describe this with a force called gravity, which would attract every body. And the famous apple that would fall down because of the force of gravity. Now, this was successful describing our universe until the 19th century, when we found out that Mercury wasn't quite exactly following this, the predictions that you would get from Newton's theory of gravity. So along came Einstein, who described gravity no longer as a force, but as a property of space and time, of space-time. He said that matter, and in fact energy, all forms of energy, would curve space-time. And so if you have a ball rolling on this curved space-time, that it would have to follow the curvature of space. And that would describe the motion of planets. And because sun and planets would actually both change the fabric of space-time, it could explain the somewhat slightly unusual motion of Mercury properly and very well. Very quickly after Einstein found this theory, Karl Schwarzschild described a situation where you have all the mass in not in a sun, but in a point. Mathematically a very simple trick, and nobody thought that this would ever occur in nature. It was just a mathematical description, the simplest thing you could calculate. But that solution of Einstein's equations had some very unusual properties. Now let's first remember why it's space-time, and that has to do with the properties of light. Already, if you have a normal situation like the sun, it curves space. Light, however, as we know, has to go always with the same speed. And so that means that if space is curved, space becomes sort of longer. Light has to go through this with still the same speed. So the speed is constant, but the length, the space, has expanded. So how do you keep velocity constant? Well, also time needs to be stretched. That's what you see here. As light goes through a bent and curved space-time, time that you measure will slightly change, the time that you infer. And that has to do with simply the fact that time is nothing that exists on its own. Time is always what you measure, and you measure it with light. And so light defines time, and as space-time changes, velocity of light stays constant, the time needs to change as well. Now, and light will be bent in the same way as planets will go around the Earth. It will follow the curvature of space-time. Now, what happens if you go to the extreme solution that Schwarzschild found? The closer you get to this central point, the faster you have to rotate to keep in balance the curvature. And of course, once you go to the closest point, what we call the event horizon, then you would see that you have to rotate with the speed of light in order to stay put, and that doesn't work. So at this certain point that we call the event horizon, light and matter will actually go into this object and disappear and never be able to come back, because you would have to escape with faster than the speed of light. In fact, what's really happening is that the space itself drags you towards the center. So it's not even that you go out and come back. Actually, space drags you into the black hole, into that point source, faster than you can travel outwards. And that's what's happening near this event horizon. And what also happens is that at this point, time and light get stretched so fast, to an infinity, that in fact time comes to a standstill and light ceases to exist, so to speak. It gets redshifted to an enormous factor to infinity that it actually stops radiating. That's why black holes have to be black. That's why I called black holes. Now, how are they created? We know a pathway to create them simply by the explosion of super big stars, 20, 30 times the mass of the sun. As they explode, the central region is condensed, matter will collapse, and will keep collapsing forever. Black holes are filled with a lot of matter, and they create a gravity that's not bigger than the star before. In fact, it's less because part of the matter is expelled. But when you get close to them, the gravity is extreme, close to the event horizon. And then you'll have to rotate with close to the speed of light, and when you get inside, you're gone forever. Now, and that's quite interesting, because now we have a real situation that creates something that is almost a point source. That probably is a point source for all practical purposes. And in the theory, that creates a singularity. So where the equations really break down when you go to the very center. And Roger Penrose nicely described this. It's amazing that we actually have singularities at the beginning and end of space and time. You have the Big Bang at the beginning, where the universe expanded out of a point, and you have sort of these black holes where space-time ends and stops. And so this is our universe that we can explore scientifically up to the Big Bang, and up to the levels of black holes. In between those singularities, our normal universe exists. And so that's what we can measure, but we cannot measure before and we cannot measure after, at least according to the theory of relativity. Now, I described to you how a stellar black hole can be made, but it turns out they're even bigger black holes, and they are in the center of galaxies. And so what you see here is a zoom into the center of our own Milky Way, and that actually led to the Nobel Prize last year by Gensel and Gaze. And what you see, if you zoom into the very center, you see stars again. And what you see is a movie over 15 years, and you see how stars move. And in the very center, one star moves particularly fast. In fact, it moves with 10,000s of kilometers per second around a central source. And that's what you see here, this orbit of this one star. It's an elliptical orbit. It's like a planet around the sun. But this is a very big star orbiting around a radio source. And from the velocity and distance of that object, you can infer that there have to be 4 million times the mass of the sun concentrated in this one point. And this is the same region now seen in the radio. The radio can see through the dust in our Milky Way, and if we zoom further into the very center, we see that at the heart of the Milky Way, there's a tiny, not so bright, but very, very small radio source, where a lot of radio emission comes from a small region. And that's where all the stars rotate around, and that's where all the mass is concentrated. And what you also can infer, and that's some calculations I did when I was essentially doing my PhD 25 years ago, that as you go higher and higher in the radio frequency regime, you come to the frequencies of hundreds of gigahertz, then you infer that if there is a black hole, that emission should come directly from near the event horizon. And that was a tantalizing sign which told me at the time, wow, something's interesting going to happen. Maybe we can use radio telescope to peer into the heart of this black hole and maybe see it. It took a little while to realize this further. Now, these black holes in the very centers of galaxies seem to be commonplace. In the 90s and the 2000s, they have been indirectly found by the action, by gravitational action, where stars were rotating very fast in the very center and gas was rotating fast. What we also found that these supermassive black holes, which probably formed from the merger of many smaller black holes in the center of galaxies, that the size of the mass is related to the size of the galaxy. The really big galaxies have big supermassive black holes, and the normal galaxies have normal supermassive black holes. And what does really massive mean? Now, if you go to the nearest, biggest galaxy we have in our local universe, and local means indeed 55 million light years away, the galaxy M87. This is the biggest galaxy, thousands of billions of stars. It was suspected to have a black hole of 3 to 6 billion times the mass of the sun. And if you go to our Milky Way, as I just described, it's much smaller, and the supermassive black hole itself is also smaller by a factor 1,000, about a factor 1,000 closer to us. And that's why those two galaxies were the prime candidates to observe, the biggest and closest champions among those black holes. And this is, as I said, where the Nobel Prize was given for. If you look at M87, this one galaxy, this was actually already discovered in the beginning of the 20th century in 1918. And you saw in this galaxy this little streak of light in the very center. And you saw something later with radio shooting out from the very center of this galaxy. And this had enormous power. These were a significant fraction of all the stars in our Milky Way. You would have to need to power this radio beam coming out of this very center. In the left part of this slide, you see a picture taken in the Netherlands with a LOFAR radio telescope, which I was involved in 10 years ago and built up here, which shows a large bubble, 120,000 light years in diameter, which is filled by plasma that shoots out from the very center, from a region that's roughly the size of our solar system. So enormous amount of energy in a very small, space. And the idea was always this has to be a supermassive black hole. Why? Because supermassive black holes can be the most efficient power generators in the universe. How does that happen? Well, you let matter fall onto a black hole because of gravitational attraction, because of friction, material falls towards the center. And, well, what happens near the event horizon? Things will get sped up to the speed of light almost. And so that means you have enormous velocities, and you can turn that velocity into thermal energy. And you can heat up gas to billions of degrees. And in fact, you can turn that way up to 40% of the rest mass energy that's stored in the matter into radiation if you're maximally efficient. And so that makes black holes the most efficient, much more efficient energy sources than stars or nuclear plants or whatever by actually a significant factor. Now, what happens near supermassive black holes, of course, because of the space-time being bent, you see that light is being curved. And that's what you see here nicely illustrated with a black hole, and you see light path around the black hole. And what's also quite interesting is that you see, in this case, you see light going, to the left, and then it turns back in front of the black hole and goes around the black hole in sort of an interesting loop. Why is this? Because that black hole is rotating. It takes space with it. And that means that light actually has to follow the rotation of space. And that is quite an interesting aspect that we, in fact, already can measure with satellites orbiting Earth, where Earth takes along with it space, lets it co-rotate, and that drags you along. And that happens in an extreme case near black holes. What also can happen is if you shoot a light ray at a black hole, it will go past the black hole, it will be bent, and will be actually forced at a very specific distance to actually rotate forever on a circle. And so that circular photon orbit defines what we call the photon sphere of black holes. And that leads to very interesting effects. Namely, that means if you have light coming in a little bit closer, it will rotate the black hole, will disappear in the event horizon. And if it's just outside that photon sphere, it will go past the black hole and will shoot out to infinity. It creates a very sharp boundary between light that will disappear in the event horizon and light that will be able to escape. And that leads actually to the structure that we published in 2000, which we called the shadow of a black hole. That if you have light shining at a black hole from all directions in a three-dimensional geometry, and that's what we think is happening in these black holes in the center of our Milky Way, which is different from the picture you might have seen in the past. You have light coming from all directions, then you'll see a dark shadow in the very center. And that reflects, it's essentially a magnified view of the darkness coming from the event horizon. And that was a clear prediction that we should see, and that size of the event horizon is proportional to the mass of the black hole, and it should be surrounded by sort of a ring of light because light rays are bunched near that photon ring. So that was something to see, and we showed that if you'd use a radio array the size of the Earth at wavelengths of 200 gigahertz, and at frequencies of 200 gigahertz and higher, and which is millimeter wavelengths, then you should be able to see that structure in the center of our Milky Way and potentially other galaxies. Now that was a clear prediction. What you actually see here, let me sort of jump over this, just to describe this. You can imagine these black holes as sort of a campfire, with light being produced around it. You can actually look through that fire, that heat, and you have this dark object in the very center. And so if you have cattle inside of a fire, you're not seeing the cattle itself, you see the shadow of it, or the darkness. You see the lack of light. And that's exactly what we're seeing in these pictures. So in that sense, that's the only way to see a black hole is by the not light that you're seeing. The only difference from a campfire and a black hole is that black holes amplify themselves. So if you look to the left top figure, you see sort of the darkness you would get from Newtonian gravity. And if you have Einstein's gravity, this darkness will become a factor 2.5 bigger. So that's the main difference. And of course, the fact that a kettle, if you put it into the fire, will heat up and it will glow at some point, while a black hole will only become darker and darker and bigger. It will never become hot in the sense. And it will actually become cooler the more higher fire you put on it. Now, you probably have seen these pictures. I show them because I saw them in the question that people submitted, pictures from Interstellar and older pictures of NASA. This is sort of a picture where you have matter go around the black hole in a thin disk. That also exists, but not as the black holes we are looking at, where light comes from all directions. And in this case, you actually see a hole in the disk which is lensed, and so that's slightly different from the situation we're looking at. Maybe we can talk about this in the Q&A. Now, to understand how black holes work, we don't rely on the simple back on the envelope calculations. We simulate them in supercomputer simulations with big codes which simulate plasma flows. In fact, they simulate magnetized plasma flows in arbitrary curved spacetimes. These are rather involved simulations that you can do, which has a lot of physics built into it. In fact, you can calculate all kinds of spacetimes. It doesn't even have to be the theory of Albert Einstein. It could be an alternative theory of gravity that we can calculate it. And what you see here is a torus of hot gas surrounding the black hole. And you see these ropes. These are the magnetic fields. And you can actually see them by looking at the polarization of light. But the polarization of light we haven't published yet, but we can simulate it. And we can simulate where the magnetic fields are. And now we let the torus of matter rotate around the supermassive black holes. Now the inner part will rotate faster than the outer part because of Kepler's law, more or less. The closer you are to a black hole mass, the faster you have to rotate. And that leads to the magnetic fields being wound up around the black hole. And that will give you something like a spaghetti bowl in this case. And very close to the very center, magnetic fields are wound up so strongly that they're being expelled. And sometimes it's actually they're dragged along by the space-time itself, and then you can actually put energy from the black hole into the rotation of magnetic fields, and that leads to matter shooting out from near the black hole. And that's what you see here. If you let this run, these simulations, after a while, you see nicely the plasma torus, which has sort of evolved, and you see matter shooting out along the rotation axis. And that explains the plasma jets that we're seeing wherever there are massive black holes. So it's a rather complicated system, but we can actually simulate it these days. And we can actually, of course, simulate how they would look like. Now, what you see here, everything is proper physics except the colors, because these are radio waves, and we assign a certain color to these radio waves because we cannot see them. There's no one-to-one translation. And so what you see here is the plasma flow. You see the hot plasma flow going around. You see the darkness of the shadow in the very center. And you saw the plasma smoke, so to speak, coming out. It's only a few % of the plasma that goes out, but it probably dominates our view of black holes, in fact, because this is where the hottest gas actually is, the one that shoots out. And so these things we can simulate very well. In fact, this simulation is a VR simulation in full 3D. So it's actually cool. You can fly through it with VR goggles on and view it from all sides. We are still trying to put this into a theme park so you can have a black hole ride or something like that to enjoy it in a physical way. Now, I showed you actually this picture was actually many radio waves, many frequencies put together. But you can actually selectively target certain regions. And if you go to high enough frequencies, then you're actually looking only at the emission coming from near the event horizon. And then this is a prediction actually that we made in 2016 for the source M87, showing that there the light would be concentrated towards the central region. And you would see that ring of light, you would see that darkness in the very shadow, in the very center, that shadow. And what you will notice, if you remember that image, of course, this came very close to what we saw in the end. Of course, what you're seeing here is not a ring. It's actually a sphere of light. Yeah? You see the light going around the black hole from all directions, and you're looking at it from a certain particular vantage point, and from wherever you look at it, you always see the ring of light being strongest sort of at the edges. There's also light in front, and the light behind is actually bent around and put into this ring. But so the central region will be significantly less dark, but it's not completely dark. Okay, so it's not really a ring and a hole, it's a shell that you're looking at. And you see it's sort of brighter on one side, and that's because the matter is rotating. In fact, that's matter in this jet. It's rotating, and therefore rotating with the speed of light. And that kicks, gives the photons a kick, and they become brighter when the matter flows towards you. And so that's why the part that's rotating towards you, you expect to see brighter. So that's the prediction, and the size on the sky is 40 microarcseconds. Okay, and so that corresponds to, Wim compared it to the wafer resolution you have. I understood we are a factor 10 better than you guys, but I'm sure you're going to beat us soon. This is like a mustard seed in New York, as seen here from Veldhoven. So that's the kind of resolution you need to have for a telescope. How do you get this? You need an Earth-sized telescope, and that technology is actually not new. It's 40 years old. It's called very long baseline interferometry. You combine a telescope around the world, and you synthesize a virtual telescope. And you can do this because you can record radio waves on hard drives. And that's exactly what we do. We are recording radio waves on hard drive, and then later bring them together in phase to synthesize what a normal dish would do. These are our telescopes. Some of them you see here, top right is one in Arizona. Then you have Hawaii to the left, belonging to our Asian colleagues. To the left, a Mexico telescope. The bottom right, telescope in Spain, where I was. And of course, I went there because they actually had the best food, I must say. And then you have the South Pole, which also is very nice, but you have to stay an entire night there. And the night, as you know, takes 6 months. So the crew, which was there, actually spent a couple of months before they're able to return after the observations. And then the big telescope in Chile, which in fact consists of 64 dishes, which are combined into one. These were the telescopes we had. We needed these telescopes because they operate at these high frequencies. They never worked together in such a big array before, so you have to make this happen. It's a big sociological as much as a technological challenge. And you want to go to high mountains because you need a dry location with very little atmosphere above you, because millimeter waves or submillimeter waves are absorbed by humidity in the air. And so that's why it's important to go to high mountains. This equipment that we installed at the telescope, there's a block down converter, so you're converting the radio frequencies down to a few gigahertz. You have an ADC where you convert it to actually digital signals, and then on the left you see, there's not an earthquake, it's just me shaking, by the way, in this film. You have hard drives, racks of hard drives, which you then can take out, and you can send it to a central location, and you actually send really big boxes of hard drives to a central location. And we are recording now 64 gigabits per second. In the first experiment, only 32 gigabits per second per telescope. So in total, it was about 4 petabytes of data that we had on hard drives. And you hope you don't miss any of these drives, because then you really miss data. And of course, to synchronize the dishes, you have an atomic clock at each site. You still have to correct the atomic clock because it's not accurate enough, and we use calibration observations of quasars, of bright sources on the sky, to actually correct the atomic clocks with our observations. Now, I always get questions, how does it really work? This is not a real image. What kind of image is this? Well, yes, it is an image in radio, of course. But in principle, it's exactly what your eye would do if it would be the size of the Earth. Unfortunately, an imperfect eye, because we don't have telescopes all over the world. So what does a normal telescope does? Imagine you have a telescope the size of the Earth. Then you have a point source. You have a plane parallel waves coming in. It will be reflected, and then it will be focused brought together in the focus. And that actually creates an interference pattern between those 2 points on your dish. And the strength of that interference tells you whether it's a perfect point source that you're looking at or a slightly extended source. If the left and the right wave I'm showing you are completely incoherent from completely different sources, then you would not see any interference pattern. If it's a point source, you would have a perfect interference. And so that tells you something about the structure of the source. And it turns out that every telescope, every radio dish, an optical dish, every camera does exactly what we're doing here. Namely, it reflects and brings light together in the focus. And that mathematical operation that you're doing there, for those of you who've been in a physics training, is a Fourier transform. Every mirror, every dish, every lens does a Fourier transform. And all we do is we measure the data at the location of where the dish is, and then we do the Fourier transform in the computer. Okay, so we do digitally what the telescope would have done in an analog way. And then, of course, you still have missing information where you have to use image processing to do this. Now, I show you how this looks like. So if you have one connection of one telescope, it measures the Fourier component in one particular direction. You get an interference pattern, essentially, in your image plane in the end. Now we're adding more and more telescope, more and more connections, more Fourier components, and then you suddenly can recover the structure of that image that we put in. And well, you can see this is not a black hole, it's a tea kettle, teapot, and we can recover that structure. So this is essentially a teapot behind the moon that we could image with such a telescope, if it would radiate at millimeter waves. We did that, and of course, the result, I have to show you the movie that we got. We did the observation in 2017. We started calibrating in 2018. We first calibrated the data on other sources to make sure we are not fooling ourselves. We were sort of not touching the real data. Then we were unboxing the data, and I'll show you a little bit more about this image processing steps later on. And it took another year until we were able to publish the result and show this movie, which actually shows a zoom into the depths of the universe. This is probably the highest resolution movie ever made in astronomy, by a factor of 1 billion, zooming in from the sky towards the constellation of Virgo, where the galaxy M87 is located at 55 million light years away. You see the LOFAR image where the bubble that's shooting out of the very center. You see the jet. And now we're looking at images that were made before with the Hubble Space Telescope, with other VLBI arrays at lower frequencies. Now we go closer and closer to the black hole. And then we saw that image, which was that image of the black hole that we published in 2019. And you saw all before, the entire 100 years before, we always saw this jet shooting out. And only when we got to the frequency where the emission comes from near the black hole, it suddenly showed up, that ring-size structure. And it's exactly at where you think the black hole should be. So that was just a magical moment to see, but also a scary moment, because the first time you saw that, you're wondering, are we fooling ourselves, or is that right? And what we're seeing here is this lensed image. It's about 100 billion kilometers in diameter, which is the size of the entire solar system, well outside Uranus, including the last pieces of gas and molecules or atoms that are produced by our sun, this gas bubble around the sun. So it really, the entire solar system would easily fit inside that black hole. It made world news around the world. I think it was 4.5 billion viewers looked at this black hole. Internet was full of jokes, all kinds of things. But of course, as I said, how can we be sure it's right? And so before we actually did anything, we gave the data to 4 independent groups to do the image processing and the image reconstruction. We do a Fourier transform. Then you have artifacts from the incomplete data that you have, which you have to then take out with standard image processing techniques. And we had 4 different groups doing this with partially calibrated data. And all 4 groups, when they finally brought the data together, they shared the images. All 4 showed that ring. We did another step of improving the calibration steps in the meantime. Then we actually made an image challenge where we gave people simulated data with rings and a disk and a double source, and we asked them to produce a pipeline. So there were image processing was done with fake data. They didn't know what it was, and then we checked how well they would reconstruct the data. And in all cases, we were able to separate, a disk from a ring or a double source and so forth. And so that was the final result. In the top row, you see 3 different image processing algorithms, 3 different groups in the end with automatic pipeline processing. And on the bottom, you see 4 different days of observations, and all giving a very consistent result. And so then we became very convinced that what we did was actually correct. And we're able and willing to publish this. We also went back to old data. Experiments were done before with much fewer telescopes, which were actually not able to give you images. But once you have an image, you can fit it to the data. And what we found that already in the 10 years before, the same ring-like structure explains the data best. And so that made us confident. And then we ran supercomputer simulations, as I described before. In fact, 60,000 images of black holes. In fact, these black holes are different orientations. They are different sizes. They are, well, actually here most of them have the correct size. They are different orientations, different spins of the black hole. So 60,000 images were made, and all of them actually showed rings and shadows, and we're fitting it to the data. We're able to extract, look which models fit best. And in fact, quite a range of models. Black holes are very generic, seem to explain the data well. So in the top row, you see 3 rather different models, astrophysically different models, strongly astrophysically different models. One with very strong magnetic field, the other one with few magnetic fields, the other one with strong rotation of the black hole, the other one with low rotation of the black hole. And all models actually accurately reproduce the data. And that's because you're really fundamentally dominated by GR and this light bending effect that overtakes everything else, including the astrophysics. And so it's a very fundamental aspect of GR to see that shadow. So in that sense, I think we are quite confident now that we are seeing really the black hole shadow and not some astrophysics. And that's an amazing feat now, because we are measuring really properties from near the event horizon. And as you've heard, we had this 2015, we had the Nobel Prize for gravitational waves. At least I think the discovery was 2015, where it's stellar mass black holes merging together. And we now have an image of a supermassive black hole. And they both give us information about the size of the region of the event horizon, more or less. And in fact, one has 60 solar masses, the other one has 66 billion solar masses, over 8 orders of magnitude. And what you see is that the event horizon size scales linearly with the mass of those objects. And that means over 8 orders of magnitude, relativity explains the behavior of black holes perfectly well, with extremely small errors. And that, I think, is quite amazing to think that something as theoretical as GR that was developed 100 years ago now covers such enormous scales in the universe and does such a great job in explaining things. Even though Einstein himself, just to correct this, never believed in black holes. So it took him a long time to actually start believing in black holes. He never predicted them. It were other people who predicted black holes. He was actually trying to disprove them mathematically. And he failed. So Einstein wasn't always right. Now, what's in the future? What's going to happen? We need more telescopes to make better images, to get more information. This year is a flight into the French Alps, the Noema array operated by IRAM, and some of our funds from the European Research Council have been used to actually put these telescopes together and to let it function as one big dish. And so in the next observing run, which will take place next month, by the way, this telescope for the first time will participate, and we get actually more information about the supermassive black hole in M87. These are 15-meter dishes that have been built on the top of this mountain, 2,500 meters, and really feels like a James Bond movie. If you're flying there, you're landing there, and it's like the evil villain's headquarter. But actually, they're pretty good people there, and with their fascinating telescope. We are trying to expand the array further. We want to put a dish into Africa because there's not a single high-frequency radio dish currently operating at Africa. So one of these dishes that you saw there is actually located in Chile right now, not being used anymore. This was sort of one of the first dishes. We want to refurbish it and put it into Africa, and so we can expand the network of telescopes and again cover more of these Fourier components and potentially also make movies of black holes in the future. I show you here a little movie of the top of this mountain, the Gamsberg Mountain in Namibia, overlooking the Namib Desert. It's the second highest mountain in the entire southwest of Africa and connects very well to the rest of the network. And you have a very dry location, as you can see. So that's a project we're trying to raise funds for at this very moment and get it going. The telescope is there, the plan is there, still looking for the money. And of course, in the long run, you want to go to space because you don't have any atmosphere in space and you can make a telescope that's bigger than Earth. And this concept that we call the event horizon image or something we worked out and published. And the idea here is, in fact, based on an original idea by a colleague in China, where you have 3 telescopes at slightly different orbits around the Earth. They will orbit at different speeds, obviously, and so they will drift apart. And so you have the separation grow, and you have the orientation change all the time. And that allows you, and what you see on the right side is sort of what we call the UV plot. This is essentially the, in the Fourier plane, the information that you cover for those people who are, understand the math a little bit. So we'll be able, by having all separations, all orientations, we will be able to cover all Fourier components and make a perfect image. No distortions by the atmosphere and complete information of at least the average image of black holes. But for M87 we could even make a movie. So what you see here is a simulation on the left of very high. You can also go to higher frequencies, terahertz. On the left you see a real movie of a simulation, how a black hole would look like. And when you average it, only when you average things, you see the shadow come out and this ring of light show up. And that's important to actually make many observations. And that's why also the first observations of M87 now from the ground is only the first step. By doing 10 more observations, we can actually increase or improve our parameter estimates by a factor 10 almost. So it's really important to average over many observations. And what you see on the right is actually relatively small dishes. And with very simple image processing, you see really sharp features of this black hole. In fact, you could also turn that into a movie if you want. And so literally, only the sky is the limit. If you make large enough VLBI array in space, we could see all the bright supermassive black holes in the universe. It's just a question of money and how much it's worth doing this. But in principle, we can see them all more or less. So let me conclude what we've learned. I think we are very convinced now that we've seen the shadow of a black hole. We are really looking into the darkness of the event horizon. And that's literally the end of space and time, where time stops. And we've looked towards the Big Bang. We're looking towards the horizon of black holes. And the question is, can we go any further? Can we go look into what's happening in a black hole? This is one of the big questions. And that's where quantum physics comes into the play, which tells us maybe there's Hawking radiation, black holes could evaporate. But still, you're not able to get much deeper than this. In fact, all the information, will get out if Hawking is right, but it will scramble in such a way that it's still sort of black holes will remain ultimate destruction machines. Of course, this was a long process to get this going. From the first idea to the image took 25 years. Everything starts with a vision, that's true. But you need to have a lot of patience, obviously. You need a strategy. You need facts to back them up because it's not that you have this idea and this vision, I have this great idea. It took like 10, 15 years convincing the community and yourself and myself to, to say that it got to happen. This must be possible. And then a lot of hard work, a lot of sociology to bring people together. And in the end, it's a lot of luck because the fact that in 2017 we got this data, we had perfect weather around the world, all the technology worked, and that is not normal when you make such a first experiment. It could have taken many years longer. Many other things could have happened in between. In fact, the last 2 years we couldn't observe because of Corona, because of technical issues, and this year, we're at the edge of being able to do this again. So it's, luck is an important element in science and in all of this. It was we needed the world, and it required a global collaboration, and it was independent institutions coming together voluntarily, and that was not always easy, but in the end it worked because we had one common vision, one common goal. Driven by science, we wanted to see that black hole, and that was an important aspect that held us together. And sometimes, I can tell you, you all work probably in big collaboration. It's not always fun. And so it's important when you start such a process to set up a framework for what I call competitive collaboration. It's important to have a competitive element in there. Everything we did actually independently twice with 2 different groups to check each other. I think that's a very important element to make sure there are no errors. And you saw that things were almost right in each team, but by cross-checking, they both got always better. And that's an important element. So work together, but also have people be a little bit in competition and make sure it stays a friendly competition. And that's not always easy. And of course, all that we had to do digitally, as most of you now work completely digital the last year. But I can tell you, and probably you've noticed this as well, it works for a long time, but it's important to occasionally see each other face to face. I hope that's going to happen, that we meet each other in real life at some point. We can chat about the things of life and science and enjoy this beautiful world that we have out there in this beautiful universe. Thank you for your attention.
Thank you, Professor Falcke. Thank you very much. I have the tendency to applaud on behalf of all the few hundreds because digital collaboration goes a long way, but the applause and the sound are also important.
Yes.
So we have a Q&A, and a series of questions came in, and I hope you're willing to
absolutely
answer them. So this is the fresh question from the. Could it be possible that one of the outcomes is that we find that the speed of light is not constant? Are there things which you can deduce if you know more?
Well, we can see that at least within like 10%, if you look at, maybe 30%, we see things happening at the distant universe where light expands, and you see actually things lighting up as there's a flash of light, and then you see a ring of light as it grows. And from that you can deduce that also in the early universe, 10,000, sometimes millions of light years away, speed of light was the same as here, to within 20-30%. Of course, we know here on Earth, speed of light is very, very constant. So I don't think that will...
and it will not originate from this type of experiments, never, like that.
Well, I mean, you could think of different people now. There's a lot of creativity. People think of different theories of gravity. What can you change? Is the Lorentz invariance violated, for example? Yeah. And so these questions are being probed, but there's no indication that this is happening. So,
another question is, when 2 black holes start to collide, do they first pull mass from each other, or is that because of their nature impossible? They simply swallow each other?
They simply no. Like if you have 2 neutron stars collide, then actually you could have matter expelled. For black holes, that's not possible. But what you have is, of course, that part of the gravitational field of the energy is radiated away as gravitational waves. So, in fact, the system does lose sort of energy via gravitational waves. Yeah.
Another question from the audience. This is a very intriguing one. We know that antimatter exists.
Yeah.
Dirac, there's also a follow-up question later, because you had the Dirac equation. There was a strange mathematical solutions which turned out to represent antimatter. But if antimatter would become a black hole, is it because gravity is the same for antimatter, or maybe not?
Yeah.
Are the properties the same, or?
Well, I think as far as we know, and that's still being studied, but antimatter has positive energy in at least in the Einstein field equations. So they would act like normal matter.
Normal matter.
And so unless you identify a matter which has negative energy, negative gravitational energy, then it would change. But as far as we know, a black hole doesn't care. Whether I've seen questions here about dark matter and whatever. So a black hole doesn't matter. Yeah. So it doesn't matter what the matter is. It's dark matter. It's antimatter. It's light. It's energy. It's any form of energy will just make the black hole grow. We don't know anything that will make a black hole shrink except Hawking radiation. But again, I've seen the question of Hawking radiation come up many, many times. Let me address this right away. Hawking radiation is a theoretical idea that has not been proven yet. It seems likely to me that this is happening, but it's also something that happens on extremely long time scales. So think of this black hole in M87. It will take 10 to the 97 years for it to evaporate from its current state. In fact, it will keep growing, and so in the end of the next 10 to the 30 years, and so it will probably become 10 to the 10, 10 to the 11, 10 to the 12 solar masses eventually, and then will take even much longer than that time scale to evaporate. And in my book, I tried to, I had a slide about the book, so to make some advertisement. So if you by the way, can show that in the end. It's the only.
Well, let's work on that. Then we go
to. I try to calculate, and I think you have to take out. That's a joke, and here, that's a book. So if one of your languages is part of it, you can read up on some of these things. Thank you. I think it's probably enough. If you take one atom out of the universe, the entire universe, every Hubble time, so every time the current age of the universe, it would still the universe itself would still evaporate faster than that black hole with Hawking radiation. Just one atom, right? It's totally staggering how low Hawking radiation is. So for all practical matters, whatever goes in stays inside.
But for all practical matters, does it mean that scientists will not find a way to discover the nothing out of a lot?
Yeah, and that's a big question. Is there any way that we transcend those boundaries? I mean, we've learned that we can do everything. Like we've expanded our horizons ever and ever, but we also discovered the last 100 years there's a limit to our knowledge. We cannot know what's happening now at M87 because all we see is what's 55 million years ago. We fundamentally cannot know what's happening now. There's a quantum uncertainty principles, right? So there's Heisenberg principle. There are certain things we cannot know. We cannot predict certain things. For example, the rotation of the Earth around the sun, is well described by Newton's and the laws of relativity. But the exact location becomes chaotic. The calculation becomes chaotic. The motion will not be chaotic after like 15 million years or something like that. So we cannot predict where the Earth will be exactly in 50 million years from now, simply because of, we would need to know now its position to within less than an atom's diameter. Yeah. And so we've learned that there are fundamental limits to knowledge in science, and so that makes it interesting. So I think we'll never be able to predict everything.
Would be a nice last sentence, but we continue
right.
still. There's an expert in the audience who said that the Einstein equations were predicted, as you said, from this Schwarzschild, I suppose was the mathematician who did something.
Well, black holes were predicted on the basis of Einstein's equation by Schwarzschild,
yeah.
Yes.
There were also two solutions, like the Dirac equation, apparently, according to this, with a -1 and a plus sign.
Right.
So, like the Dirac
Yes.
equation predicted antiparticles, does the plus sign predict something intriguing?
Yes, yeah, indeed, and that's what people talk about. There are also white holes. That could be a solution where where everything can only go out and never go in. That would be the exact opposite to black holes.
Okay.
In fact, if you put a black hole and a white hole together, then you would have wormholes. You know, you've all heard about them. Einstein-Rosen bridges, as they were originally called, and you could potentially transverse them and go from one to the other. Now that's a mathematical possibility. At this point, we don't know how a white hole could ever form. We don't have any idea how a wormhole could form and how it would be stable. If you watch a sci-fi movie, then you always need a certain type of matter. In fact, you have to invent a certain type of matter that doesn't exist to create wormholes. So for all practical purposes at this moment, it's not clear that wormholes or white holes exist, whether they're part of physical reality or just mathematics. At this point, they're just mathematics. And not everything that you see in mathematics becomes reality. And that's the job of us physicists to figure out, what is real and what is not.
There's enormous amount of angular momentum in these things.
Yeah.
When they fall in, they spiral up. Your shadow is perfectly round.
Yes.
Is that a matter of luck that the momentum is this way, or are there two non-related things, the brightness of your radiation and the enormous amount of angular momentum in the system?
That's a property of GR. And if you have no rotation in the black hole, let me say that up front, then you expect the shadow to be perfectly round. And in fact, you can use the roundness of that shadow to actually put limits on any alternative theories of black holes. Because a black hole only has two numbers. And we say a black hole doesn't have hair. It has the mass and the rotation and the charge, but we usually ignore that in astrophysical contexts. And so only two numbers describe the size and the shape. And if the black hole rotates very fast and it's still almost perfectly round shadow, it gets a little dent, like 5%, but that's all there is. So a black hole always has to be almost perfectly round. It could be an egg shape only if you have additional parameters that are not in the theory of Einstein. That's exactly what we're looking for. If we would have found a triangular black hole or a highly elliptical one, we'd have been totally psyched and excited to see that, because then we could have thrown Einstein into the dustbin but unfortunately that didn't happen.
Maybe you would not have been believed. You had to do
I agree, but it would have tantalized us, and we would have done many more studies. But right now, Einstein has won again.
We have a question from someone who knows the Radboud University.
That's good.
That your group and the university is trying to deploy a radio telescope on the moon. Is
Yes.
that one reason to extend the baseline for this work?
Well, you could think about putting one of these telescopes on the moon. The current experiment we have, in fact, this is a radio experiment called NCLE on board the Chinese satellite, which already is behind the moon, called the Chechao, the satellite. It's a communication satellite behind the moon, going from the back of the moon towards Earth. And we are there to measure low-frequency radio waves. And that's not to look at the end of space and time, but to look at the beginning of space and time, namely at the beginning of the universe, the dark ages of the universe. When the universe expanded, it was filled with hydrogen, and that hydrogen would emit this famous 21 centimeter line, but that's got redshifted from 21 centimeters, expanded due to the expansion of the universe to actually many meters. So we observe between like 10 to 30 megahertz. That's what we want to measure light from the dark phase of the universe when the universe was only filled with hydrogen. And the best place to do that is, in fact, on the surface of the moon, behind the moon, because there's no interference, there's a stable ground, and sort of the quietest place on Earth is behind the moon. And that's where you want to be with this experiment.
I want to stop this part of the Q&A. I also will announce that we continue after the formal closure of this hour with a Q&A based on the questions that came in. Professor Falcke was willing to do that, so we will continue. But I want to thank you very much. Great talk, great subject. Extremely well presented. I'm sure it has been an inspiration. And we have a...
He's still there. He's coming back.
Still there. He's coming back. I'm moving out of the screen. Attention about how ASML was generated also from a concept, from an idea.
Yes.
A few people, 30 people, starting in the 1980s, believing that they could do lithography and make it work.
Yes.
And now we're with 22,000. So things can grow.
It helps if you can earn money with your science, right? So that makes, it facilitates the growth.
Okay.
Wonderful, thank you.
Thank you very much. And thank you all for being at this Tech Talk. You will follow the announcement. Next month we will expect to also have a Tech Talk lined up. Our colleagues from Asia, I hope you enjoyed this opportunity, and please give your reactions to the organization if you think this initiative is worthwhile also for you. And with this, I want to close this hour. Thank you very much for those who have to go and have to do work. And then we continue with the Q&A. Bye-bye. Yes. Let's whatever you want. You can. I have here better reading. This is
okay.
The big
oh,
letter.
you have a bigger one. Okay, good. So let's. Where do we start? Oh, there were. Well, there was a question. Pascal Semer-Jeff. Oh, can the HT be used to study the structures of the earliest galaxies, or the cosmic microwave background? No, not the cosmic microwave background. There you have to go to other. Because the cosmic microwave background is happening on large scales. Black holes are on small scales. But we can look at potentially black holes in the early universe, but then we need to go to space. So if you want to see black holes better in the early universe, we have to do a space mission. Paul Bryan asked whether we can, we have one image now, and we have a library of images. Could we train an algorithm to identify images of black holes? We tried something similar. We have a machine learning approach where we use actually a library of simulated black hole images and then see which one fits best. And you give me an image of a black hole, I tell you what the parameters of that black hole are. And that seems to work quite well. But again, in order to get really good information of black holes, you have to have a space mission. So, because right now the resolution is a bit too small to have many images. Well, Paul van der Veen asked what the steps in the image processing are. I think I tried to explain this. It's essentially a Fourier transform that you first do. Again, the same thing that a normal dish would do. You create an image, and then you get a dirty image. And that contains all the scratches. And so that image that you would get is like you take a telescope and you put dark spots on your dish, right? You make scratches in your lens, right? Then you don't get perfect images, but you get really blurry images. But you know exactly where the scratches are and how they actually change the image, and that's what you can calculate and take out and divide out. And this is essentially the heart of the image processing, which in fact is standard image processing, and even your cameras do this. So in that sense, I heard people say, it's not a real image. Well, your digital camera isn't a real image either. This is a one-time achievement, or do we want to do this more often? Yes, we want to, as I said, because in order to sample more rotations. So on the shadow, again, you look at this campfire, right? The flames will change all the time, but the kettle will be the same. The teapot that's in the fire. And so by having many more images, you get a perfect image of the teapot, and the flames will average out. So already from one snapshot, you can see the teapot quite well, but it will be better if you have more measurements. And then we get better parameters and constraints on GR, and we're testing also alternative theories. And so really the big question is, how do you get gravity and quantum physics together? Now that's going wrong at the edge of black holes. And we can test it to some degree, but maybe the big progress will not come from the fact that we show deviation, because we don't know at what scale this will happen, deviation due to quantum gravity effects near black holes. That could be on an epsilon around the event horizon, then it would be not measurable at all. Then it would probably be never measurable ever, okay? But if it's happening on scales of the Schwarzschild scale, then we'd be able to see it. If it's just a few percent or a fraction of a percent, that we'll be able to detect. So that is a way forward, why we want to do more data, get more data. And in the end, science is also a bit like art. It's inspiration. And so we hope that now many theorists now start working on making testable predictions of alternative theories of gravity. And so maybe there's one bright mind who has, whose theory will not be testable by our experiment, but who'll get another idea which will be the big breakthrough in quantum gravity research. So
Will it be always Messier 87, or do you hunt for
No.
other black holes as the black hole in our
good
Milky
point.
Way?
I forgot to mention this. Of course, the big breakthrough is still the center of our Milky Way, which is the biggest one. It's the one where we know the mass the best. We have the best handle. It's just, it's a very, the fire crackles much faster around such a star than in M87. That's why it was easier to do M87 first. Those two sources will always be at the forefront of our experiments. But if you go to space, there'll be more. But the highest resolution, the most best resolved images will always be these two.
Okay, M87 was a lucky one that we
M87
have so
was a lucky
close,
shot, and such a star will be the scientific
correct.
workhorse for the decades to come. Yeah. So that's Reinder Plug, Rob Fazen. Ask whether we can use this to, not only visualize black holes, or also dark matter. No. As I said before, it doesn't matter what's in a black hole.
But there's something, you mentioned everything falls in.
Yes.
So the volume of intensity is somewhat connected by the volume of things. And if you know dark matter should be there, we have not seen it, but it has a something which is a gravitational analog. So why then can you not deduce it from absolute things?
Let me correct myself slightly. There is an idea that dark matter consists of so-called axions, certain very long wavelengths, elementary low energy particles, and they could accumulate around black holes, and they would then change the gravitational potential around a black hole. It would not be a point source, it would be a point source plus a sausage, so to speak, around it. And that could happen on a few percent level, and that would change the appearance of the shadow. It would change the metric of space-time, indeed. So that's one way. I forgot about this. Thank you for reminding me. Indeed would be a way to find some evidence of dark matter. But in galaxies or so, where most of the dark matter is, we wouldn't know. There's an interesting question by Romulus Mihalka. What happens with the matter? Particles, radiation absorbed by a black hole. What happens? Well, all we know, it ends up in the point, in the central singularity, and it will be smaller than an atom, so we don't know what form of matter energy that is. The way I always describe it is that actually all form of matter will be turned into space-time curvature. So I have to see space-time curvature as a form of energy. And we know we can turn matter into light and light into matter. And what's happening here is now that light and matter gets turned into space-time geometry. That's all I can say at this point. Wow, there's a long question by Ruben Gertz.
You can select one of the four sub-questions.
Oh, it was about the perfect circle. We answered that one already. Are we showing a particular frequency range? I think I explained that as well, because we have to go near the event horizon to see where the light is shining on it. How many variables you need for this image?
How many fudge parameters?
Well, it depends on what, there are variables of the image processing algorithm that we try to constrain. We try to relatively constant, but they do have a few indeed. But they don't change the structure that you see in terms of that it's a ring. We can see almost with naked eye, right? So I think it's a fairly relatively robust eye. Looking at the raw data, I mean. And a black hole itself has two free parameters, the spin and the mass. And then, of course, the orientation. How are you looking at it? And then the astrophysics can change the intensity distribution. It will not change the shadow. And so in the end, in the library, we had like 4 or 5 parameters changing over that we're varying. I think it can be a few more. If you're honest. But the good thing is that most of these parameters don't change the appearance. And that's the beauty of GR. It's these two parameters, spin and mass. Is this an actual image? I've addressed this several times by Ruben Heckens. I think it's as much an actual image as you can do in radio waves as possible, with limited information, of course.
But color was
and the color,
the intensity is the brightness.
Color, yes, the color is. I try to say that the color is intensity. In fact, if you look at our prediction in 2000, I chose that color for artistic reasons, because it was reflecting heat.
Yeah.
And it stuck. And that's why, you know, even NASA now is plotting it in red colors. And I think it's a better, you know, it could have been pink, it could have been green, but I think that would not have captured people's imagination as much, right? No. So it's a color scale, obviously. But it's radio, and radio is, of course, a very red light. In that sense, it's almost far infrared, right? We are very close to far infrared. And so in that sense, red is also not completely wrong.
But you mentioned that the total radio intensity being radiated in this process was more than the energy radiated by all of our stars in the Milky Way?
No. The power generated by the supermassive black hole is enormous. There's some quasars which do the same thing, which have like 30 times the energy of all stars in a galaxy is radiated, is liberated. In fact, most of that in kinetic power in these jets near black holes. But the amount of radiation that we receive is just, I think I want to calculate if you have a hair which is 1 millimeter, you let it fall by 1 millimeter, that's the kinetic energy that we've received in this in this process. Yeah. So it's almost nothing. So yes. Rupal Basak asked about the new targets. I mentioned the center of the Milky Way. Shekhar Gupta.
He had a question here.
Asking about why we said it's rotating clockwise. I think that is one of the weakest conclusions that we drew. In principle, the intensity distribution is the least secure thing, because as we know, gas can rotate, and it could be just, you know, by chance that one part of this ring lights up now. It could change with time. So the size of the ring shouldn't, but the intensity distribution should. But if it's indeed brighter at the bottom, if that sort of persists, then that's because of relativistic beaming, light moving towards us. And the other part actually moves away from us. So that's how you would find out. So that's one thing that explained.
Propose one or two more questions, and then we then we stop.
Well, can we do a similar interferometry, Simon Koop, at optical wavelengths? Yes, that's happening. Unfortunately, we cannot store optical wavelengths on hard drives. That makes it much harder to do. The next challenge I explained. Create micro black holes. No, that's very hard. They would evaporate immediately by Hawking radiation, and they haven't shown up in any particle physics experiments. What happens to anything that enters into a black hole? Well, turn into space-time geometry. Hawking radiation I mentioned. What will happen in the long run? Will the universe gradually become to only include black holes? I think yes. I think in the end, over 10 to the 100 years, the universe will probably only consist of supermassive black holes, which then will slowly radiate away. It's a very sour view of the universe, but who would have predicted the Big Bang in the first place? So I think that's so let's hope for miracles and wonders. When do we get a video? Well, anytime from now until the next 10 years. Space VLBI I mentioned. What's the orientation of the disk? Well, most of the emission that we see is optically thin. That's why the orientation has an impact, but not such a super strong impact. And that's why it's a bit harder to constrain. Can we image a merger of two black holes? Gravitational waves try to do this, but we probably not be able to image it. They would both have to have radio emission. That'd be cool. If we have really big radio array in the very future, we know these two supermassive black holes will merge, and they both have radio emission. In principle, we could see that, but the chance is very small. I think what happens when two black holes meet? Oh, that sounds like a joke, actually. Well, two black holes go in a bar and meet. I don't know what the joke is, but I'll think about it. Well, they produce gravitational waves, obviously. Okay. Well, sorry I can't answer all the questions.
No, that's okay. This is great. Thanks once more. And to those who are still there, have a nice day. And we see each other again.
Okay.
Bye-bye.
Bye-bye.